Hello everyone, my name is Junyu Zhou. I am a PhD student from the University of Pennsylvania. Here, I am happy to share our work, Bosehedral, a compiler optimization for Bosonic quantum computing. This is a joint work with AWS Quantum Technologies and IBM Quantum. To begin with, I want to introduce the Bosonic quantum system. Many of you may be familiar with the qubit system. It can be described by a two-dimensional Hilbert space with spaces 0 and 1. Then a valid quantum state is a linear combination of 0 and 1. For example, phi equals to alpha 0 plus beta 1. On the right is a bosonic system, also called Q-mode. It lies in an infinite dimensional Hilbert space. The basis is called the Fock basis, starting from ground state 0 and contains infinite elements. You can think of them as the energy eigenstate of a harmonic oscillator. A bosonic quantum state is the linear combination of Fock bases with normalization. Now, let's see how to use bosonic Q-mode to do computation. Firstly, we introduce the creation and annihilation operators. The creation operator ak-dagger lifts the energy eigenstate from n to n plus 1, and annihilation operator ak lowers the energy eigenstate from n to n minus 1. With those two operators, we can construct several bosonic quantum gates. For example, the squeezing gate S, the phase shifter R, the displacement D, and a 2-Q-mode gate beam splitter BS. Their expression in terms of ak-dagger and ak are shown on the right. In addition, a measurement symbol m is shown at the bottom. Next, I want to introduce a famous algorithm, the Gaussian boson sampling, or GBS, that demonstrates the quantum supremacy using bosonic quantum computing. A quantum circuit of GBS is shown on the slide. Firstly, all the Q-mode are prepared in a ground state, and state preparation is injecting photons into each Q-mode using squeezing gate. Then, all the photons will go through a linear interferometer constructed by phase shifter and beam splitter. Finally, the photon numbers are measured at the end of the circuit. By repeating this process, the configuration of photon number will shape a distribution, and directly calculating this distribution using the classical computer will encounter calculating a Hafnian function, which is a sharp p-hard problem. Thus, GBS can be used to speed up many tasks. Firstly, it can speed up many NP-hard graph problems, such as finding the dense subgraph or maximum clique. Secondly, it can naturally simulate bosonic systems and has the application of calculating the vibration spectra. To encode those problems, one of the most important steps is to get a problem-specific unitary matrix U and encode it into the linear interferometer using phase shifters and beam splitters. This step contains most of the quantum gates in the GBS program, and let's see how to do it. First, we decompose the unitary matrix using this formula. The capital lambda stands for a diagonal matrix, and TMM with parameters theta and phi can be viewed as a two-dimensional unitary rotation. The theta is the rotation angle, and phi is the phase shift. M and N specify the Q-mode index this rotation is acting on. Then we will use a phase shifter to encode phi and a beam splitter to encode theta. We call this phase shifter together with the beam splitter a MZI block. Finally, we join those MZI blocks together to build the linear interferometer that achieve the unitary transformation U. And in this form, n-dimensional unitary matrix needs n Q-modes to decompose. Each Q-mode is correspond to one column of the matrix. This decomposition can be also viewed in an inverse form using the matrix elimination. Here is a real example. we have a three-dimensional unitary matrix. In step 1, the green element is eliminated by the yellow element, using a unitary rotation between columns 1 and 2. Thus, on the middle, a MZI block on Q mode 1 and 2 is applied. Since unitary rotation preserves the norm of the row, the amplitude of the green element is observed by the yellow element. This is visualized on the right, where we use an arrow from node 1 points to node 2, indicating amplitude accumulation. In step 2, a elimination happens on columns 2 and 3, make the last row as well as the last column complete the elimination, and is removed from the remaining process. Finally, elimination in step 3 makes this unitary matrix diagonal. Those MZI used in elimination are exactly what we used in previous unitary decomposition, and joining them together give us the linear interferometer as shown in the bottom. Based on this, researchers have already established two decomposition formats, the triangular format and rectangular format, because the circuit built from the MZI block looks like a triangle and a rectangle. Both of them required a fixed number of MZI blocks, which is around n squared over 2, where n is the size of the unitary matrix. This compilation format has naturally encountered some limitations in ISCA device. Firstly, they only allow MZI block acting on logically adjacent Q mode, for example in this red box. However, the MZI block in this blue box is invalid, although Q mode 1 and 3 may be physically connected, as shown on the right. Secondly, the current compilation lacks an initial Q mode mapping process. The Q modes are randomly assigned to the problem. Thirdly, ISCA devices often have quantum noise, especially for 2 Q mode quantum gates. Instead of using a fixed number of quantum gates, we should consider a potential gate reduction to mitigate the physical error. We notice that there are many qubit-based compilers based on qubit gate matrix representation can achieve quantum gate reduction, but they cannot be directly applied to the bosonic quantum computing scenario, since each Q-mode gate has an infinite dimensional gate matrix. Thus, a unique bosonic compiler optimization is needed. Our optimization goals are clear. First, we will consider the hardware structure and high-level representation of the unitary matrix to give a flexible quantum gate decomposition. Second, we aim to find a good initial logical to physical Q-mode mapping. Thirdly, we adopt a probabilistic method to achieve quantum gate reduction. Let's come to the first goal, optimizing the gate decomposition. So why different decomposition of matrix matters? We demonstrate it using a numerical example. On the left, there is a three-dimensional unitary matrix, and we want to decompose the row in the red box. We can use orange element to eliminate green element. The green element is numerically larger than the orange element, thus the rotation angle theta of beam splitter is large. If we use purple element to eliminate the green element, since the green element is numerically smaller than the purple element, the angle theta is small, and we call this large-small elimination pair. And small beam splitter are close to identity, which can be dropped to mitigate physical error. And we should notice that the current compiler only allows the decomposition on the top. However, some ISCA devices support the decomposition at the bottom. Thus, we want to maximize the large-small elimination pair by exploring the ISCA device structure to achieve more gate reduction. To achieve optimization, the first step is to create a template. Suppose we will decompose a n-dimensional unitary matrix on the top. We eliminate the row in the red box according to those arrows. Then, an elimination pattern can be summarized. We have highlighted the corresponding elements in the same color. It has 3 rows. The row in the middle, we call it main path. Other 2, we call them branches. The arrow stands for how the elimination going, also stands for the amplitude accumulation, which means the amplitude on the main path will grow larger and larger. Thus, when we use the main path eliminate branches, a large small elimination pair will be created, which generates the beam splitter close to identity. Step 2 is to embed this template into ISCA device. For example, a 2-dimensional Q-mode lattice. We can fit the template in a zigzag pattern. The red dots stand for the Q-mode on main path, and blue dots stand for Q-mode on branches. Step 3 is to select the substructure after embedding, because some of the Q-mode may be redundant. This is the decomposition optimization. Next, we will tackle the Q-mode mapping problems. So why does the mapping matters? We have already selected our device structure and we are maximizing the large-small elimination pair using amplitude accumulation on the main path. But if we initially put numerically large element on the main path and small element on the branches, this will increase the probability that we get a large-small elimination pair and thus further maximize the beam splitter that is close to the identity. We have proved that this Q-mode mapping has no execution overhead. Suppose we have a unitary matrix, and we permute it using the permutation matrix PR and PC. Instead of executing the PR and PC on the quantum circuit, we can relabel the logical Q-mode at the beginning and relabel the output at the end. Now, we are going to map our unitary matrix. First, divide the unitary matrix according to main path and branches. And we want to assign large entry into the main path region and small entry into the branches region. Then, we calculate the norm in the orange region, which is the square norm. And we switch the red and blue columns. If this switching resulted in a larger norm in the orange region, we are going to accept this switch. The last step is to permute this row with the larger orange region to the bottom. Finally, we are going to introduce our quantum gate dropping method. As we mentioned before, the beam splitter with small rotation angle is close to identity, and we are going to safely drop them to mitigate the physical error. You may notice that dropping those small beam splitters will slightly change the algorithmic formulation of the problem. To control the algorithmic error, we are going to reconstruct our approximation unitary and measure the trace distance with the original unitary. Here is how we drop our quantum gates. First, we will decompose the unitary matrix and get those parameters theta. Then we will establish a probability distribution using this formula. If the theta has small amplitudes, then the probability is small and is more likely to be dropped from the circuit. Next, I will show our evaluation. We have tested our compiler on those 4 benchmarks, and we have 2 metrics. First, we use Jason-Shannon divergence (JSD) to measure the distance of sample distribution between the ISCA device and fault-tolerant device. Notice that all of them are simulated on a classical computer by setting different gate fidelity. Second, we adapt an end-to-end matrix. For example, the probability of successfully finding a click or getting the right molecule spectrum. We first test our compiler on 6x6 Q-mode lattice, which means a lattice has 6 rows and 6 columns of Q-mode. We set the quantum gate fidelity from 90% to 99%. Compared with the baseline compiler, Our optimized compiler achieved a 26% reduction in sample distance to the ideal sample from fault-tolerant device, and we achieve around 30% of quantum gate reduction. Also, we have tested the hardware impact. We compiled the task to 5x7 and 3x8 lattice respectively. The average sample distance reduction is 27%. Next, we examine the end-to-end performance. For the graph problem, it shows that our compiler increases the probability of finding the right subgraph by 69% compared with the baseline compiler. And for the graph similarity problem, the graph distance has increased by 135% for the benchmark, which makes the classification easier. For the vibration molecule problem, we can see that the samples from the baseline compiler have a huge shift and low correlation with the ideal distribution, while our compiler achieves a high correlation and has a similar shape with the ideal distribution. In addition, experiment results shows our compiler is scalable. The quantum gate drop ratio is approaching 27% when increasing the QMOL number. And even for a 500 QMOL problem, our compiler takes less than 20 minutes to compile. Thank you for your listening. If you are interested in our project, please join our talk.